mostly we put it on paper and don't think about the fact anymore that even if I just say f of x is x squared, I need some memory to store that function. Okay, by f, right? On what does that depend? What is the minimum amount of parameters to memorize that function? And of course, everybody will ask, and does this my function generalize to other data? That's like the machine learning question. Okay. I can already tell you that I'm not going to answer this question, but I'm going to give you the route to answer this question. But before we go there, let's start where we are. So here's what David McKay did. Okay, David McKay in his book, chapter 40 of Information Theory, Inference, and Learning, it's in the end of the talk in my slides, says, okay, we have a perceptron. For me, it's just an encoder. Okay, so in the Shannon model, everybody should know, it's basically you have this model where communication is modeled as, hey, some sender has a message, it goes to an encoder, then becomes a signal. As it becomes a signal, you have to transmit it, let's say, from cell phone to cell phone. Noise is added, usually in the form of Gaussian noise, given central limit theorem. And then signal prime comes out, and then it's decoded into message prime. And the big question is, when is message prime equal message? Obviously, when you have a communication, right? So when did nothing change? What do I have to do in decoder and encoder so that the channel cannot destroy my message? So let's do the same thing for neural networks. So what we really have here is a little different. Okay, we abuse the model a little bit, okay? In fact, there's a little bit of a discussion. I totally understand if you come after the lecture and say, but, yeah, I know. There's a sort of a 99% accuracy here. So we don't have a sender, really. What we have is labels, right? And then we have an externality, which is called data. So we train the machine learning with something to create weights, which is parameters, in fact, right? So now these parameters, in fact, by the way, if you had a zip algorithm, that would be very similar, right? So you had data and you would zip it. All you do is you create the parameters for unzip, okay? So just to see about this analogy. So here's what we do. We create data, we encode it, we create some weights. So now these weights go through a channel which we don't care about, okay? So it's identity. There's no noise right now. I know this is the part where I say, there actually might be, but for now, there's no noise. So now we have a decoder. The decoder is the same perceptron again, except it takes our weights in and the data externally and recreates labels prime, okay? So this is now, of course, if you go back to the machine learning part, train on test, okay? So we didn't do any generalization yet. Right now, all we are asking is, if you have some training data, how well can the data to labeling function be remembered, okay? And that is, you have the labels and you have the data and you trained and you encoded the data to labeling function in your weights. Given your weights and the data again, how well can we reproduce the labels? That's just the same question as the message that I sent, which is the labels. Can they be reproduced? So that is the question I'm going to investigate for the next 20 slides or so, okay? So that is for now. And please blend out any sort of generalization or anything. We'll come to that. For now, we're asking ourselves, what can I learn? So let's start with the perceptron. Let's be very simple. So again, you have these xi to xn. They are summed up with some weights. And then the question is, are they greater or equal than a threshold? So let's do this for some concrete numbers, okay? So 0.9x, 1 plus 2x is greater than 1, and so on. So now you create a linear, what's called a linear separation with a perceptron, okay? So now you could ask yourself, okay, first of all, in n points, right? Let's say you have n points. How many labels can you create for that? How many functions could you actually do? How many linear separation can there be in general, right? Not with one, but in general. Well, it's pretty clear, right? That's just saying for two classes, you just have either a 0 assigned or a 1 assigned to each of the points. And so that the input space gives you 2 to the power of n labels, right? And also now we know where the perceptual learning comes from being exponential and so on. Same thing. So basically you have n points that can be either in class 1 or in class 0, okay? So for now also we keep it, because it's a perceptron, We can only do binary classification. We keep it to binary classification. So now given that, if we want to know how many parameters do we need for all the 2 to the power of n, that becomes a more interesting question. Before we go into the interesting deep question on this, let's try this. Let's try this for Boolean function, right? So we have a Boolean function of 2 variables, x1 and x2, right? So we've done this probably in computer architecture, right? So 0, 0, and so on. So now how many Boolean functions are there for 2 variables? Well, there are 2 to the power of n labels, and so n is the variables, right? So there are 4 labels. But then also for 4 labels, you can store 2 to the power of 2 to the power of n functions, right? So that grows quickly. So what you have is you have for 2 variables, you have 4 points to label, right? But then 16 functions. So now of these 16 functions, it turns out, if you just do that, like by hand, that you can actually model all of these 16 functions but 2, so 14 of the 16 function, with 1 threshold, right? So in fact, it turns out all but 2 functions can be linearly separated, right? So the 2 that cannot be, and it's not even a surprise, is XOR and not XOR. Not XOR, by the way, is the equal sign, which makes total sense, because obviously in order to determine if something is equal, you need to go through everything, right? So XOR and non-XOR are the 2 where you actually need 2 linear separations. So now, you might have seen this before, right? So, but in a different way, and it's been used in a very confusing way, okay? So we tried, even with people who work on this, like Peter Bartlett and so on, to get a better grip on this, and this is what we came up with. So the VC dimension, right, is sort of a capacity. The VC dimension is the maximum integer d, such that some data set of cardinality d can be shattered by f, right? So that means shattered by f means that any arbitrary labeling can be represented as a hypothesis in f. If there's the maximum holds, that's infinite capacity. So what they do, actually, why did I skip? Let me see, sorry. No, actually, it's right. So, so what did they do is nothing else but ask themselves, okay, given the function, right? So let's say I have a perceptron. How many can I, what can I do, right? But also, it's not, so what they require is interesting. What they require is general position, right? And general position just means in k-dimensional space, in general position, if any subset, I mean, you have seen this before, small equals k is linearly independent, okay? That just means there's no sort of set of linear equations that can solve this. But general position is not random, okay? So the confusion here is that they took a checkerboard pattern and wiggled it a little bit. Now, that's not random. It's in general position, but it's not random. Taking an XOR and wiggling it a little bit will still need exactly 2 separations. Taking an AND and wiggling a little bit will still need only 1 separation. Okay, taking a checkerboard pattern is taking a special structure. Okay, and in fact, kind of, no, this is not it. But anyway, so, but for the single perceptron, that's good enough. For the single perceptron, you can say, okay, in general position, because we only have linear separation, how good can we do? And so, interestingly enough, most people in the US credit Cover for this proof. That's not wrong. Actually, it is wrong because Cover cited about 15, or it's a bunch of people. I don't know. I don't want to lie. I don't know exactly how many, but you see this where there's, oh, and other people before me, and then this long thing of citations already did that. Just they didn't connect it to neural networks, okay? And so I looked for the first one to do this. So Schläfli was in 1852. It's a book that, unbelievable, the Berkeley Library had. So somebody must have looked at this before. It's in German, very hard even for me to understand, even though I'm native speaker of German, but it's Swiss German math in terms that, you know, we all have never heard because it's terms from 1852, but it's absolutely the same proof. He's asking, in a space, how many linear separations can I do? And he has this function called TNK. Okay, so we call it TNK for T like threshold. He has a different notion for it. But basically, the nature of the function is this. TNK indicates the number of distinct threshold functions on endpoints in general position in k dimensions. Okay? So now you got to understand, and this is going to be later, that k dimensions is nothing else but k parameters, right? So, and if you look at this function, hey, that makes a lot of sense, right? So if n and k, right? So n is sort of the number of input points you can have in general position, and k is the number of parameters you can have, and then you basically match sort of your coordinate axis honestly against those, right? So now if you go n divided by k, when obviously when k is greater than n, oh, you can do everything, right? You can model all of them, right? So interestingly enough, when n equals k, that's still exactly the truth. But now the more interesting part is what happens is if n is smaller than k, right? And if n is smaller, if k is smaller than n, sorry, if k is smaller than n, that means you have less parameters than points. You can still do it for many of them, okay? And of course, people like Cover and McKay, information theorists, they see the almost all here right away, okay? But we'll take a look in this in depth. And so this is what they did. They said, okay, let's take a look. So first of all, this axis here, oops, that makes no sense. I didn't touch this one, right? Okay, yeah. That seemed correlated, but really it wasn't causal. So, so the point is, basically, it looks like this here. I mean, everybody agrees when n is when n is smaller than k or equals k, we have this. And so now he looks at the second order. He says, hey, if we take a look at this closer, right, how does this function actually evolve? And that's actually an absolute miracle in some way if you like math. It's a Pascal triangle. So 6 plus 8 is 14. 22 is 14 plus 16, 30, and so on, right? So that's your Pascal triangle. And if somebody thinks Galton board, yes, correct. So what McKay does is he just says, hey, this is like a Galton board. So honestly, all we have to do is we accumulate the Gaussian here, and then we'll have n divided by k. And at 2k, we'll have 50%. I didn't like the way he did it. So we proved it inductively, and that's also interesting because you can actually do that. But ultimately, what happens is the second order of this function goes like this: that when you can guarantee that when n divided by k is 2, that you have exactly 50% accuracy. Okay, exactly. Okay, which is interesting. And not only this. If your memory, and we'll see later, if your memory efficiency is less because of a practical implementation, that point will be twice here. It's really, really cool. It just works. So for now, right now, this n divided by n equals k, or n divided by k is 1, will be your VC dimension, okay? But this is basically all the work, again, information theory, inference, and learning algorithms. It's an amazing book. Everything I tell you here is a 6-page chapter. And then from there on, it took me a bunch of time to get to what I'm trying to do next, which is let's generalize from the perceptron to actual neural networks. Okay? So now you got to have a couple problems here, because when most people think about neural networks, they think about this. Okay? First hidden layer, second hidden layer, and so on. Well, let's look at XOR again. Well, one way to solve XOR with more than one perceptron is to basically do a layered approach. So you can actually do the math. This will solve XOR. Okay? But there's another way. It's called a shortcut network. This will solve XOR as well. It's not your standard architecture. And yeah, what's going on? Okay. I'm not even touching this. That's why I'm really surprised. I'm touching this, you know. Anyway, so this has less parameters, though, right? And now I really need to count them. Yeah, this doesn't seem the laptop. This is maybe at the other end. Okay, let me first of all, because... Oh, did I run out of power maybe? Ah. In the worst case, I can do this on the whiteboard, don't worry. But it's more fun for you if I don't. So, okay, so now it's charging. Yeah.
No, we're good.
Okay, so we're not able to project the slides right from this? No. Okay. Yeah, just pull them up, because I'm not sure why this actually just stopped working. Because we record, I mean, Keynote. It's yeah, so the laptop crashed. Okay, let's see what's faster. So this is crashing right now.
Okay, can you get it up?
That's
Laptop not coming back up?
the laptop is not coming back up, so I have no idea what's going on. That's a lot more than.
Do you specialize in finding?
Oh, this is the heat. Interesting. Okay. The good news is I have no animations or anything, so it's so cool.
Oh, sorry.
Right.
We come prepared. 4 laptops.
I know.
2 fire chargers, and we end up having to use them all 3 cameras
So
and smartphones.
here we go.
Yeah, it's just going to take a
And
minute,
5
I
PAs.
think.
Plum. Here we go. So now it just needs to appear there. What's going on? Why doesn't it appear there?
Stop asking questions.
Okay.
You display settings on? Turn on your preferences.
Now I might have to actually do a chalkboard. I don't know.
Anybody else have a Mac we could use? A couple.
A couple, yeah, it's good.
Add that to the list of things we bring to class, right?
Give it one more try because this would just work, right? So does it?
Right.
Ah, here we go. Perfect.
Perfect.
Oh, actually, I think this is it's still glitching.
It is just glitching. Like it detects.
I don't think it's the laptop.
That was me, but it's being weird.
I think I just
Okay, so you found the problem? Okay, so well, can you solve it in?
switch over to the camera part.
Yeah.
You switch over to the overhead camera, right?
Oh,
And
this.
you just video the screen.
Yeah, just video screen the thing.
Either one.
Here, Jerry, it's like, turn the
And they can show up any screen at all. Fine.
I mean, I can I can go by board, but
Here we go.
Yeah, you go.
here we go. Well, whatever. You know, I will do whatever works.
Technology.
Zoom in a bit.
Okay.
Sorry.
All right, beautiful.
Okay, good. Well, whatever works.
Position it properly.
Oh, it's gonna topple, so you gotta.
The one doesn't
You
want
have
to
to move the computer. We were close. Oh, okay.
Well, that's fine because it doesn't work anyway. Okay, so all we needed was to count the numbers here. So while they're working on it, right? This is 1, 2, 3, 4, 5, 6, and this is 1, 2, 3, 4, 5. Okay. So we just for XOR we already saved the parameter, and we will need a theory that is independent of this architecture, right? So it just shows you already how simple stuff can impact you. This is called a shortcut network, by the way, and it's been very popular in recent times because guess what? Shortcut networks go deep very fast. Okay, so shortcut networks go deep very fast. Obviously, people are interested in them. I say obviously, but who never. So now, when we analyze neural networks, we cannot analyze them in general position. And here's why. Because you have more than just linear separation, right? That was probably the point why we didn't have a lot of analysis of neural networks, because perceptron, yeah, you just use linear separation. Linear algebra will give you the answer. So now the problem is with the nonlinear, you could, for example, solve XOR with one parameter if you just, do use X squared. Like, so, boop, done, XOR solved. So instead of general position, we need something else, right? And so this is also very important to know. Pattern plus a little bit of noise is maybe general position, but it's not what we need. What we need is what we call random position. In the paper, links is still chaotic position, but I got slapped on the wrist and it was right. So it's actually random position. So random position is you cannot predict anything, okay? So you have 1 point, you know nothing about all the other points. Or you have n-1 points, you know nothing about the last point, okay? It's also interesting to think about this because what can a neural network do when you give them completely random points? What kind of prediction can it do? None, obviously. I give you random numbers. The best thing you can do is memorize them. Ha, model works, right? So the random position is obviously also general position, just to be consistent. And the only valid distribution, unfortunately, that would give us that random position is the uniform distribution. Now, I want to point out, and that's really interesting. First of all, we never really have a uniform distribution, but the point is we put uniform distributions into neural network learners, and they crashed, okay? I'm just giving you how on earth did nobody ever try this? We had networks like TensorFlow and Keras for certain parameters crash on us. And that gives us the indication that this is probably not will work when we actually measure this, okay? They crashed. So we actually do the measurements with a Gaussian. That means we add a little bit of certainty. It's not completely uniform. But the point is that's the only way we can actually do practical measurements, because for some reason, which is not mathematical, it's some bug, things can crash, okay? So that was very interesting for us. Anyway, so in theory, we should do uniform distribution, right? So now we remember the perceptron, right? So we have these two critical points. One is where we can, for sure, 100% memorize all the points we put in. And the second one is what McKay pointed out, and he called capacity, where it's basically up until almost this point, you can memorize almost all data in there, right? So now, how do we scale these two critical points? Well, first of all, it wasn't clear that they also exist in a neural network, but the point is that was my intuition, so I just went for that. And it turns out to be true. So, but we call these 2 points. This was sort of for perceptron, it was the VC dimension, but we call this for now the lossless memory dimension. It's lossless memory because if you just use it as memory, you can put stuff in and take stuff out, and there's no loss. And the second one was we call it the McKay dimension, right? Which is actually the capacity in a channel capacity way. But the interesting thing is you cannot guarantee that you put stuff in and it comes out the way it came out. So label doesn't equal label prime, but for most cases, it most probably will, right? So that's sort of the information thing. So we gave this a formal definition. We say lossless memory dimension, and lossless memory dimension obviously implies VC dimension, but unfortunately, the math frameworks aren't as compatible that this is actually true anymore. So I actually need to take that back. But the one way to look at it as a conceptual way is to say it's a stricter VC dimension. VC dimension, you can use you can invent a structure and put that in. We don't allow this. The structure needs to be random, okay? So no structure. So now, the second critical point is basically, we defined this basically based on McKay. That is basically saying, and I think it's a good point to have, right? So if a binary classifier, right? When you have 50% error, it starts to be, you don't have to use that thing anymore. Anything better than 50%, obviously, there's still maybe some application to use it. So that's not a stupid point to have to define, right? So basically the point is, if you train something and you're above McKay dimension, you might as well not even start training, right? So that's why, because you're wasting cycles on learning something that you cannot memorize it, right? So it's again. So that's basically what this is. So now, how do we generalize from lossless memory dimension, the lossless memory dimension, from the one single perceptron to the neural network? And we went through, if you read the original paper that I sent you, extreme length of like hand waviness that that was, I think okay, except then things became so easy when we just like abstracted and said, hey, just measure this all in bits. We use it as memory anyway, so we have a measurement unit called bits, right? And the moment you measure things in bits, we know first the first thing, which is there's no universal lossless compression, okay? So that means is with n bits, you can, in the best case, memorize n bits, right? So this is actually what memory does, right? Now, in the best case, if you have DRAM, it sucks, as you know. It's not as good. You have to do something. But if you have a neural network and you do a lot of tricks with it, then the same thing happens. So you will actually cut down your memory efficiency. And you can measure that, and we did. So now, the question, however, is, the first thing you would say, okay, but we have a lot of bits in the network, right? So we just, they're all doubles, right? So we have doubles, and then the bias is a double. So all of these bits should do something. And the answer is, the way we use neural networks, the answer is no. The answer is we can only use one bit. And this is actually a very simple way of showing this. Is we have this dot product. Can you all see this? Okay. So we have in a single perceptron, we have this dot product, right? Which is just doing this. Sorry. Asking, are you greater than some threshold? Okay. So now what you got to think about is the following. Let's put the threshold to 0, just for fun, because, right? So we asked, is it greater than 0? Okay, actually that's fine. So now, what's interesting here is when we look at this, we can do the following. So the xi we can control. They're the signal. They're the data. The xi are the xi. But what we can do is just a little trick, which is we say wi is nothing else but a sine times the absolute value of that thing, right? So let's do that. So that is sine times the absolute value of the weight. Okay, this is what we just did. And so now you only have to ask one simple question. Who in that equation, or what, but I like to have it personalized, makes the decision? Okay. So now, the signal, we can't do anything with the signal, right? So let's put the signal somewhere, here, okay, in our coordinate system. That's our signal. And let's say this is cat, right? But our label function says this needs to be cat and this is dog, okay? So what now happens, what can you do with the absolute value of this weight? Nothing. You can put it down or up, but you can never cross the threshold of the axis. And that was the whole point of linear separation, right? That we model the axis. So the point is here, the only thing that makes a point go from where it is to the other axis, sort of crossing the linear threshold divide, is the sign. With the sign -1, which is just, oh, I should put this in here. It's -1 and 1. With a sign -1 and 1, you can make the cat that's here be here. That's the only thing you can do. That makes the decision in the neural networks. That means however many bits you put in here, it's just wiggling within the quadrant, right? That doesn't do anything. The only thing that does something is that as sign, or as a physicist say, spin, right? Up and down. And of course it's -1 and 1, because if you put 0, then everything goes away. But the point is, -1 and 1 is two symbols in an alphabet, so it's 1 bit. So now, what do we do with the bias, right? Is the bias so much more powerful? No. We do the same trick again. Now phi conveniently isn't 0, because we made it 0 here, right? And you'll then figure out that what you can do is, when you have this, you can do the same thing. You say phi is nothing else but this, a sign bit times the phi, right? And then all you do is you just divide by phi, and you'll see is a greater or -1 is the same thing. So let's actually write this down. Sorry. I know if you see this. Ugh. I'm writing from the wrong angle. Okay. Here we go. So what you do is you xy, sy, wi greater is sign, and then you just say, here, like the physicist. So what this does is you have a local scalar, there's a weight, it wiggles locally, and this wiggles all of them, right? So it can take an entire set of points that we locally wiggled around and swap the whole thing. But still, S is only an element, sorry, what am I doing here? Is only an element of -1 and 1. So that's how powerful the weights and the sign bit and the perceptron are. The decisions are made by the signs. And that's interesting, right? So now we have how many bits the perceptron can model. It's exactly the number of parameters. Now, since that's true, we already know that when we combine perceptrons, each one, the maximum it can do is the number of bits in each perceptron, and you add them all together, done. Okay. So now the McKay dimension is a little more interesting. So the McKay dimension, basically what we assume now is the best case, right? So since we assume the best case, we'll say each perceptron actually models exactly, it has its own contribution as 1 bit, right? So make sure it models 1 point. So we have this is the best case, right? There's no better case. So now the question is, that means that if each perceptron, each parameter is exactly doing its work maximally well, then obviously we can still go better than the individual perceptron, right? So that means in the best case network, each weight corresponds to binary decision for each input, and then doubling the amount of points results in 2 points per individual weight. We just have 2 points per this weight. And now what's interesting here is the following. We can go back to a Pascal triangle and figure something out by induction that McKay didn't see, which is kind of cool sometimes. Where's the function? Here. Okay. So, for example, let's say n equals k. We are at 8. Now we double n and keep k constant. That means we need to stay in this k3 column, and then we go from 3 to 6. 1, 2, 3, 32. So 32 is exactly half of 64, right? So if n equaled k, we will be at 64 for 6, 6. But if you have half the k and double the n, then we are at 6, 3, and that's 32. So what that means is, now we go back to the original thing. And that you can prove by induction, just that this always holds for all rows and columns, right? And then what you find out is that this is true, right? So what's true is t to an n is half of 2t to n, right? So that means if each perceptron is maximally doing its work, well, then the McKay dimension scales linearly, right? That follows the McKay dimension is actually twice the lossless memory dimension. And so that's important. So now in theory, we saw this. But if you measure a lossless memory dimension that's less effective than 1 bit per bit, but let's say 8.8 bits per bit, which is quite often the case, then you will see that we're not at 2, but at 1.6. It's actually twice the empirical measurement, which is super useful. Because that means we don't have to do all the curve measurement. We only measure until we have the first time where a function could not be remembered. That saves a lot of compute, right? So now we can formulate this as a little law, which is like, hey, everything is linear, honestly. I mean, after all the intro. And it's just basically both points scale linearly. So now, I want to go into a little more what this actually means. First of all, what it means is, hey, if you have a three-layer MLP, we know exactly what the capacity is at this point, right? The best way capacity is this. So now, interestingly enough, a three-layer MLP is actually optimal. It actually will exactly have this capacity. We measured lots of them. So the typical three-layer MLP, or I think this is speech lingo, right? Three-layer MLP. I think they use another word, which is like input layer, hidden layer, output layer, right? Is use this formula done, okay? So unit of measurement is obviously bits, right? So now we did a little illustration. You'll see basically all you do is you count all the parameters, and you see, okay, that's what you can model, right? So now obviously the criticism will be, yeah, but I don't know how much data I actually need for my function. And the answer to that is yes and no. The answer to that in this talk, I will not give you the answer. The other answer is I'm working on this, and for text data, for example, you can really well approximate it. It's really nice. For images, it's a little harder, but there's also stuff that can be done. So I mean, ultimately, nothing is perfect the moment you do it for real, right? So, and then we just did some experimental validation. I basically said, okay, look, I came up with this cool theory, beat me, okay? I have a best case scenario. If you can be better, I will stop talking. I did this for a little bit, and well, all the measurements always looked like this. Basically, this is the theory, and then they ramped up hidden units as parameters, and they never came to the limit. And then they ramped up. This was the memory dimension, and then we had the McKay dimension. They ramped up hidden units and never came to the limit. And then they ramped up dimensionality to lossless memory dimension. So there was all kinds of ways you can improve parameters or not. Ultimately, hey, nobody empirically beat me. I mean, they only tried for a couple of weeks, to be frank, but I was like, that's what I wanted. Challenge me. So now, the conclusion of the theory part is we can totally explain neural networks as storing a function from data to labels requires a certain amount of bits, okay? We have these two critical points, and they have been called phase transitions. If you're a physicist, that makes sense. In the sense that really sort of everything below lossless memory is solid. Everything between lossless memory and the second order phase transition, which is the McKay dimension, is kind of liquid. And the next after that, you can't predict, so it's gas, right? So I'm just saying, for people who have that intuition, that makes a lot of sense to them. So, and there is a paper that actually predicted this like a long time ago. There will be phase transitions in this network. So, this should be random position. But also, by the way, all of these experiments where I said beat me, it's in the paper. It's a 69-line Python script to measure your own capacity of your own machine learner. I mean, you can go ahead and really do, okay? So if you find, hey, I did better, I stored more bits than I thought, than you said, then tell me. So now, practical implications are a lot more interesting. So the upper limit, so this gives us an upper limit independent of task and data, right? So we can now, as I said before, we can look at stuff and say, okay, if I add this kind of thing, is this better or worse in terms of capacity, right? We can test architectures against each other. We can do all kinds of stuff. And of course, we can try to work on estimation, what I just said, of the parameters you give the data set. But even more, I really just talked about perceptrons and special versions of perceptrons. Of course, I had to do this because if you want to try something analytically, you got to constrain yourself really deeply. But hey, the methodology of measuring the memory of that function is completely general. It's in fact very universal, very, very universal. You could think about this as f of x is x squared. You got to store this somewhere, right? Either, as I said, on paper in your brain or on a computer. So measuring how much, it's basically like lines of code in some way too, right? So it's just measuring how many bits, can you do. So, and that is interesting. So what we actually do when we do this, because we're measuring in bits, is we say, what's the equivalent decision tree of my neural network, right? Right. So that's basically the point. So now we have a way to convert them into each other too. So there's a bunch of things that come out of this, and so then we actually did those measurements. So again, the characteristic curve, which I call it this way, because hey, if you're an electrical engineer and you buy some parts, and I've done this, people know I have a startup on speech recognition stuff. You get the characteristic curves of a capacitor, for example, which exactly looks like this in theory. Obviously, why? Well, guess why? Because this, right? So you get the characteristic curve of a certain part, right? And a little bit people are like, are you doing all this theory now? No, this is engineering. Engineering is, we know how a part behaves. Engineering is how machine learning, how this personal machine learner behaves. We can measure it. It's not guessing try and error. It's still enough try and error anyway, right? It's not, even the electric circuit design is not completely solved. But the point is we need to start thinking about this in more general terms. That's what I say. So now we have this characteristic curve in theory. How does this compare to real curves? Here, we measured them. This is scikit-learn 3-layer MLP. And I have to say one thing. We sent, and you can see this on their GitHub, we sent them a big congratulations. We sent them, you are the best implementation of neural networks that we know. Because not only do you take random functions, you also have the best characteristic curve. And Keras, we don't want to talk about that, but there are a couple of things. TensorFlow is kind of in the middle. Now I can actually go and do this kind of thing, right? So input dimension 3, input dimension 4, it's just basically how you wiggle the weights around, how you wiggle the parameters around to have different number of weights. But what happens is you see this, and of course the curve goes a little beyond the lossless memory because we have to sample. The point is, we are trying to the power of n combinations of exponential runtime. So we got a sample. But the interesting thing is, we're not sampling from an unknown PDF. We are sampling from a random distribution. That's a well-known, problem. Much better to do that. So, by the way, if you use my script to measure your own machine learner, it looks like this. Congratulations, I want to know about it. This is really the best machine learner I've seen in a long time. So now you're probably all itching for the question, what happened when you added more layers, right? Well, what do you think? This is for 3 layers. This is input, input, hidden, output. What happens when you do more hidden layers? What do you think happens? Now, given you've seen my talk. You added more parameters, but how efficient are they? Right? Because the point is they can be maximally 1-bit efficient. But since they are dependent on the decision of the previous layer, what do you think happens?
It gets closer to the theoretical curve with the thing, right?
Pretty much. So 2 things. The more parameters you add, you get closer to the theoretical curve anyway, but not in layers. If you add it in layers, each layer will get to the theoretical curve. So if you add more in the broad, you will actually get to the theoretical curve. But if you add in the depth, you get exponential decay in the number of layers. So now you need an explanation for why do these networks work so well for images, which I'm working on. And I have an idea of this. This is basically, okay, this is not a result yet, but basically the way I think about this is, if you think about sensors, how they work, then you've got noise times content, right? And that's actually Helmholtz free energy. But the point is, when you have that, it makes total sense that the further layers of the deep learner are error-correcting codes on the previous layers. So what happens is deep networks work so well for images, especially convolutional deep networks, because they model all the noise, right? And then error-correct towards the target function to get the noise out, right? But we are running these experiments right now. It actually looks quite well. Otherwise, I wouldn't tell you about this. But this makes the most sense to me, because if you measure capacity, you get exponential decay because, hey, decisions dependent on other decisions are not independent decisions.
What do you mean by exponential decay?
What is this? You get less and less efficiency in each bit, right? It's not n divided by k is 1 for those. It's n divided by k is 0.5, and then you already start. Yeah.
Is this according to empirical evidence?
Yes, it's all empirical evidence, yeah. Yeah, not, well, I don't know. Actually, that would be interesting to do analytically. That's what we were talking about.
So there's a famous theorem for Boolean functions, right?
Okay.
Which is often being cited in deep learning theory of famous, I forget what it is, you should know which one. It's basically saying that if you have a Boolean function, if you have the layers, and let's say you can model some function within some precision, then if you remove a single layer, then there is an exponential increase in the number of weights you need.
Oh.
To get the same precision.
Yeah, and okay. And I bet you we can find some mapping. That would be interesting.
So that's sort of contradiction with what you're saying.
No, I think it's, well, let's talk about this offline, but I think it doesn't contradict. It just actually, so what I learned is you gotta, there's all these viewpoints. I think in many ways, for example, physics sees a lot of things already, except you gotta then turn around, say what they see is because we do this. Because you gotta see is when they look at nature, they don't know the algorithm. When we create algorithms, and then look at them. We actually look at sort of the same, we also kind of look at nature, but in fact we created it, so, you know, stuff like this. Let's talk about this, I'm very interested in this. So the point is though, here's one more thing that you're all itching about, right? Does my function data labels generalize? So first of all, I'm taking the physicist standpoint and say universally, no. Done, right? Universally speaking, you can never generalize, okay? Why? Well, just think about it. You learn 1,000,000 coin tosses. Can you predict the millions in one coin toss? If you have all independent events, if you have a flat distribution, you cannot predict. Interestingly enough, you can still have a capacity to learn all of these coin tosses. But so capacity and generalization, I basically draw a line here, which is a conceptual line I'm drawing, which I can see where people say, hey, we need to put them back together, okay? But for me right now, I'm only worried about capacity. And the point is that I'm drawing this line. Now, of course, people will say, but in reality, and you just said this, there is no uniform distribution, so you can always learn something. True, okay? But the major point for me is, and in this work, this is completely data task independent. And when we talk about generalization, we talk about basically what information theory gives you, right? How compressible is a signal is generalization, right? So a generalization is just reducing bits. So that's information theory. And you know, you can try to merge the two. For example, as Tishby, you might have heard about him, he's the information bottleneck. And I buy his information bottleneck for unsupervised learning. That makes a lot of sense, because that's what it was invented for. Well, it's basically saying, hey, let's put generalization and the amount of parameters together and try to find the optimum. But here my problem is, with this one, is we have the amount of parameters. We know them. And so like again, maybe I'm wrong on this, but the point is, yeah, I'm going to meet him soon. He's currently right now in Berkeley, so I got to talk about him. He's arguing that neural networks do this automatically. Might be, but for me, I think it's, first of all, from an engineering standpoint, smarter to separate the two, okay? With capacity, you want to optimize that your network works. You want to debug your network. You want to make sure it does what it does. And then you go on the data and see how compressible things are, how generalizable, because guess what? These curves, They're all on random distributions, right? So now you say, but an image is not random. Yes, right. Unless you put complete noise in it, it's not random. So what will happen with the curve is it goes this way. It's going to be the same shape, except now instead of 1 bit per bit with randomness, you can actually store 4 bit per bit because, hey, they're all redundant. They're dependent on each other. And if you're lucky, we can use this dependency in a smart way. Okay, we can. Exactly. So it's going to go this way, right? So now this is basically how I see generalization. I want to untangle it for now from this. Obviously, there's one counterargument. The counterargument is to say, yeah, but if I know the structure of my data, I can be smart and build something. Obviously. So we do all the time, right? If you have enough assumptions, you can just maybe explicitly model it. You don't even need machine learning. Because I think the interesting trick about machine learning is that we have a totally coherent, uniform structure like a CUDA card that is just a repetition of 1 million units. And yet, we can use that to model whatever complicated thing. If you start to doing architecture, maybe you can get a little bit out of it. But in reality, I think mostly you're losing bits. So yeah, that's what it is. So for image processing, however, we have this bias because most people do computer vision. And this was always my pet peeve, and Picture knows this. It's like, hey, yeah, deep learning works for computer vision. And the way they did it was actually very smart. And I think we start to be able to explain why it works for computer vision. But we assume it's automatically generalized to everything else. And that might not be right. So talking about that, there's a bunch of future work. First of all, everything I showed you here was just for threshold gates, right? So RBF networks, for example, used in physics, they use Gaussian, they use kernel. Well, what RBF stands for, functions. Exactly, thank you. And so they're smooth, so we don't know exactly what happens. Obviously, as a computer scientist, I would say, hey, we don't have smoothness on the computer anyway, but still, they might be able to use more bits, okay, instead than not this. Recursive networks, by the way, and I think that was thanks to Big Shah, somebody else already worked on this and figured out they just work the same way. It's just a recursion. But also, this could be explained with Shannon theory anyway, because you can have a memory channel, right? So if you don't have memory in the channel, it's an ID, and you just go back and forth. It must be the same, because we know that a memoryless channel, if you have feedback, it doesn't change anything. So adversarial examples are connected to capacity. That's work I'm currently doing with Beaulieu and Donson in Berkeley. Beaulieu is the person, I don't know if you know this paper with the stop signs, right? So this is very relevant. The point is, you have an autonomous car, and okay, yeah, the guy threw in front, I mean, the person, we have this terrible accident, but in reality, there's a much, much bigger problem. The bigger problem is you have a stop sign detector, and the car needs to stop at the stop sign. So now you add a little bit of noise to the stop sign, and nobody can explain why the car doesn't stop anymore. Well, I said I can. Because the point is, there might be different ways of doing adversarial example, but one guaranteed way of making the network fail is because we have, so now in my car, I have reserved a certain number of bits to memorize my F data to labels, right? So these bits are now in my car, and I talk to a Tesla boss and say, ha, it works, 99% accuracy, you can totally deploy. Perfect. Except that certain number of bits can be overflowed. You know, we can take data that is more complex, and then we get an overflow. And that overflow, of course, gives you random results, right? And that's the whole point. So now we get an arms race. You say, okay, and that's the current consistent with this theory. Knowledge is, okay, you also got to train stop signs with noise, right? Yeah, that makes sense. Reserve more bits for your data, F data to labels. But what's interesting about that is, how much noise are we going to reserve? Because it's an arms race. Because obviously, 100% noise won't be a stop sign anymore, right? So the better way to do this, and this is what we are developing, is a filter. You basically like a diet, right? You say, if the voltage is too high, shortcut this thing. Don't even put it in, right? So, and it's interesting, because this is a universal flaw of machine learning right now that is not seen. Okay, you can basically, based on the Turing test. So let's do a Turing test. Let's put a chatbot, the best chatbot we have, whatever, Watson, in front and behind the wall and a person. Here's how I will find out that it's a machine learner versus a person. I will put in long random strings. And then I should actually iterate through the sentences that come out of that machine learner, because we will overblow the complexity of what typically goes in, unless they have a filter for that. The person will just say, huh? What are you doing, dude? Are you testing if I'm a machine? So I won the Turing test, right? So that basically is a universal exploit against every single deployed machine learner that we have right now. And by the way, if you want to know whether it works with my image thing that I did in my PhD, yes, it does. I even in GIMP, the point is you put in enough noisy image, you're basically host. So the interesting thing is there's absolutely a connection to adversarial examples. And I do like the fact that we have an explanation for it. So the next point is that curve. I show this in Livermore labs, and they're like, that's such a universal curve. I'm like, what do you mean? Because what we understand here is nothing. If you said this is universal to machine learners, God, this is pretty universal because machine learners is like AI, right? It's intelligence. So in general, obviously, what we have here is something. So how does this curve map to capacitors? Well, you put capacity here and voltage here, right? So what you have is the capacity will stay 100%, and you will be able to store all electrons that come in. But when your voltage goes over a certain amount, some will go through. And if you do enough, it's going to explode. But that's a different story. But obviously, a capacitor is nothing but molecules inside this capacitor that will store electrons. So that's right. So that I just made the connection to chemistry. And in physics, I have, there's a Nature paper, and I'm working with this guy. He's at KTH. He had a paper out that said, liquids are characterized by the fact that they ooze out bits. Right? Okay. And so basically, it's this part, right? So there's an interesting connection, and I think this goes very, very deep. And I'm happy to explore it with you if you like. Anyway, that's all I wanted to say. Except if you go down, thank you so much for all the people who helped with this. First of all, buy the McKay book or get it online because it's amazing. And then it's a very good book on neural networks. And then there's a bunch of people, who I talked to, including Big Shovraj, who was very helpful on developing this. Anyway, thanks for listening. And I'm here the rest of the day. Let me know any questions you have. I'm pretty sure you will. So thank you. Yeah.